Hello everyone, I am James Raja. I am the faculty of IISc Academy. Now I am going to teach you the fundamentals in the semiconductor physics. Now this is a very interesting topic and it is very easy one too. You have around 9 to 12 marks allotted for this particular topic, and it's going to be very interesting, and if you know the formula, cracking these questions is going to be very easy and simple. Now we are going to learn from the basics, which is semiconductor physics. Now when you consider material division, it is divided into a conductor, a semiconductor, as well as an insulator. Conductor, a semiconductor, as well as an insulator. Now, when we talk about carrying electrons, conducting the electrical energy, if you take a conductor, all the time it conducts. If you take an insulator, all the time it does not conduct. Now, we don't want something to happen all the time. Under a particular condition, I want the conduction to happen. In such cases, semiconductor is an ideal material. So under certain conditions it will conduct, under certain conditions it will not conduct. For example, when I talk about a PN junction, if I forward bias the diode, conduction happens. If I reverse bias the diode, the conduction does not happen. So this semiconductor is an ideal material which is used for current conduction. Now in this semiconductor we have two divisions, p-type as well as n-type. Now when you add a huge amount of p-type impurity to a semiconductor, it becomes a p-type semiconductor. And when you add a huge amount of n-type impurity in a semiconductor, it becomes a n-type semiconductor. That means huge in the sense the concentration should be 10 to the power 10 times greater than the other impurity. We can consider it in this way. Okay. Now what are the types, what are the few examples for a n-type impurity? Phosphorus, arsenic and antimony. So they are some components which are rich in electrons. So phosphorus, arsenic and antimony are some very good examples for n-type impurity. They are rich in electrons. So you wanted a semiconductor to be a n-type semiconductor, then you have to go for adding up any one of these three impurities to the semiconductor. Similarly, examples for p-type: boron, aluminium, gallium and indium. Boron, aluminium, indium and gallium. Okay, so these are the classifications of p-type and n-type semiconductor. You have to be very thorough in this classification because most of the questions are based on this fundamental semiconductor physics. Okay. Now, coming to semiconductor physics, one of the most important question that is asked in couple of years is, having given a semiconductor, what is the electron concentration and what is the hole concentration? Now for this you have to use a very important significant formula, that is electron concentration multiplied by hole concentration is square of the intrinsic concentration, a very important formula. you need to by heart this, understand this. Electron concentration times hole concentration is equal to square of intrinsic concentration. That means in most of the question the intrinsic concentration will be given and the hole concentration will be given. You will be asked to find the electron concentration, or you will be given the intrinsic concentration and electron concentration, you will be asked to find the hole concentration. So this formula is a very important formula. Now in semiconductor physics we introduce a word donor concentration and the acceptor concentration, ND, NA. Now this donor concentration is approximately equal to the electron concentration. So if you are given a donor concentration, you can approximate it to the electron concentration, N. Similarly, we come across acceptor concentration. This can be approximated to the hole concentration. Got it? Now, having sufficient knowledge in this particular stuff, you can able to find out the electron concentration or the hole concentration, having given any one concentration and the intrinsic concentration. Now coming to the N-type semiconductor. Coming to the N-type semiconductor. Now, for example, the donor concentration is given. Let us take. Now we can approximate it to N. We can approximate it to N. Now, an intrinsic concentration is also given. Now, how to find out the hole concentration? N times P is equal to Ni square. Now, we are asked to find out the hole concentration. So, P is equal to Ni square by N. Now, the donor concentration is approximately equal to the electron concentration. So, P is equal to Ni square by N. Okay, so having given donor concentration and the intrinsic concentration, you can find N and P with this formula, where N, the electron concentration, is donor concentration, and P, the holes present in the semiconductor, is Ni square divided by Nd. This is a very important formula. Now coming to the P-type semiconductor. Coming to the P-type semiconductor, you will be given the donor concentration. For example, let us say the donor concentration is given, then I can say the holes is approximately equal to the donor concentration. P is approximately equal to the donor concentration, which is, acceptor concentration, which is Na. Now, coming to the same old formula, N times P is equal to Ni square. Now, we are interested in finding N. So, N is equal to Ni square divided by P. Now, P is approximately equal to the acceptor concentration. So, N is equal to Ni square divided by Na. So, having given the Na and having given Ni, I can find out P and I can find out N. So be it a N-type semiconductor or a P-type semiconductor, you must be in a position to find out N and P, to find out the number of holes present in the semiconductor and number of electrons present in the semiconductor. Okay, so having given a N-type semiconductor, The number of electrons is Nd, number of holes Ni square by Nd. Having given a p-type semiconductor, number of holes is Na, number of electrons Ni square divided by Na. Is that okay? Now, how to identify whether the semiconductor is a p-type semiconductor or n-type? Because in the question, whether it is a p-type or semiconductor will not be straight away given. So you must be able to identify what type of semiconductor it is. If a semiconductor is doped with a donor impurity, then it is going to be an n-type semiconductor. If it is doped with an acceptor impurity, then it's going to be a p-type semiconductor. So you must be in a position to classify, to correctly identify what type of semiconductor it is. Then you have to go for finding out the value of n and p. Okay, now coming to the second topic, I am going to teach you about Einstein relation. Einstein relation. Einstein equation. Now, this Einstein equation is actually an equation which consists of diffusion constant, mobility, and the thermal voltage. Now, using this Einstein equation, having given a diffusion constant, you can find out the mobility, or having given the mobility, you can find out the diffusion constant. Take down the equation for it. It's going to be dP by mu p is equal to dN by mu n is equal to kT by q is equal to Vt. This is going to be equal to 26 millivolt at 27 degree Celsius. Okay, so this is a very important equation for calculating the diffusion coefficient or for calculating the mobility. Is that okay? So you may be given the thermal voltage Vt, dP is diffusion coefficient of a hole, mu p is the mobility of a hole, dN is the diffusion coefficient of an electron, mu n is the mobility of an electron, Vt is the thermal voltage. At room temperature 27 degrees Celsius, it's going to be approximately equal to 26 millivolt. Is it okay? Now this is a very important equation for calculating the diffusion coefficient, or having given a diffusion coefficient, the mobility for an electron or for a hole. Now, coming to the semiconductor physics, now when the electron hole recombination happens, the energy is released. It's a very important thing you need to understand. When an electron and hole recombines, this results in a release of energy. Now, in what way the energy is released? Is it released in the form of a heat, or is it released in the form of a light? Now, if the energy is released in the form of heat, I classify that as an indirect band gap semiconductor. If the energy is released in the form of a light, I call it as a direct band gap semiconductor. So semiconductor is of two types. Based on the energy band gap level. A direct band gap and indirect band gap. During the recombination, when the energy is released in the form of a light, then such semiconductors are called as direct band gap semiconductors. recombination happens and when the energy is released in the form of heat, I can classify that kind of semiconductor as an indirect bandgap semiconductor. So this is a very important physics you need to understand in semiconductor theory. Now, what are the examples for energy released in the form of light and form of heat? Now, if you take a ordinary p-n junction diode, the electron hole recombines, and here the energy is released in the form of a heat. Now, if I want to give an example for a indirect bandgap semiconductor, then I can give p-n junction diode as a very good example. Now, p-n junction diode is normally made up of silicon or germanium. Is it okay? Now, coming to the direct bandgap semiconductor, here when the electron hole recombination happens, the energy is released in the form of a light. For example, I can say light emitting diode. Now, what is the difference between a normal p-n junction diode and a light emitting diode? This is the only difference. p-n junction diode comes under the classification of an indirect bandgap semiconductor, whereas a light emitting diode comes under the classification of a direct bandgap semiconductor. So in a p-n junction diode, electron hole recombination happens, but when you just touch and see the p-n junction diode, which is operating for a long time, you feel heat being released. Now when you come talk about a LED, here the energy is released in the form of a light. Okay, so for a direct bandgap, an example is LED. For an indirect bandgap, the example is a normal p-n junction diode. Is it okay? Now, when we talk about the physics of a light emitting diode and a p-n junction diode, for example, what are the type of materials that can be used for making p-n junction, for making a light emitting diode? Now, direct bandgap materials examples: indium, gallium, arsenic. These are the kind of IN, GA, SP, IN, indium, gallium. These are the examples for direct bandgap semiconductor. Silicon, germanium are some of the examples for indirect bandgap semiconductor. So if you use these kind of materials, indium, gallium, aluminum, all these materials, you will have light emitted as a form of the energy released. Here you have the heat emitted in the form of the energy released. Now, another important content I wanted to tell you is, you have an atom existing in the ground state. Now, then you introduce energy in this atom. When an energy is absorbed by this atom, you are introducing an energy, and this energy is absorbed by this atom. Now, when absorption takes place, this is taken to the excited level. So, the initial state is called the ground state, and the secondary state is called the excited state. So you need to understand this theory very much. When an energy is observed by an atom, the atom is taken to the excited level. And it stays in that excited level for few nanoseconds, for a very short period of time. And after that time, it will again come down to the ground state by releasing the energy it holds. Okay, so after the lifetime, it releases the energy that it contains, and then it comes back to the original state, which is the ground state. Now, for example, I'm introducing a light energy with a wavelength lambda to this atom, and it is taken to the excited level. For example, I say this energy level is E1, this energy level is E2. Now, atom which is existing in the energy level E1 is taken to the excited state E2 by means of a light whose wavelength lambda is incident on this atom. A light of wavelength lambda is incident on this atom. The atom observes the energy. It is taken up to the excited state E2 from E1. Now, what is the band gap energy level? EG. We call it energy band gap. EG. This EG is going to be equal to E2 minus E1. So when wavelength lambda light is incident on the atom, it is taken to the excited state E2. Now the energy band gap is given by EG, which is nothing but the difference between the energy levels E2 and E1. Now, there is a relation between the wavelength that is incident on the atom and the energy band gap EG. There is a relation. Now I am going to give you this relation. You can take down this relation. The wavelength should be lesser or equal to 1.24, I'm sorry, divided by the EG band gap energy. Okay, now this is going to be in the units of electron volt, and wavelength is going to be in the units of micrometer. This is a very important relation. Now, having given the EG, you must be in a position to know the maximum wavelength, or having given the wavelength, you must be in a position to know the maximum elevation the atom is taken to. Okay, so this formula is very important. EG will be mostly given in electron volt, and lambda will be mostly given in micrometer. Is it okay? Now, coming to the current density. Current density J is given by sigma times E. Current density is given by sigma E, where sigma is the conductivity and E is the applied electric field. The conductivity is given by N Q mu. This is the formula to compute the conductivity. Now, N is the electron concentration, Q is the charge of the electron, and mu is the mobility of the electron. Having given these details, you must be in a position to compute conductivity. And having known conductivity, and if you know the applied electric field, you can find the current density. It's a very important formula. Now, as I told you, the N-type impurities and P-type impurities. You must know N-type impurities of phosphorus, arsenic and antimony, whereas P-type impurities boron, aluminium, gallium and indium. Now coming to the electron energy level band gap, EG. This is very important. You must be knowing these levels for certain semiconductors, silicon, for germanium and GaAs. You have to remember this because there are several questions based on these details. You can take down. Eg is gonna be equal to 1.1 electron volt for a silicon. For a silicon, the band gap energy is 1.1 electron volt. For germanium, it is going to be 0.67 electron volt. For gallium arsenide, it's going to be 1.41 electron volt. And for insulator, it's going to be very large. That is the very reason why you are not able to introduce conduction in the insulator. However you introduce the energy, it's very hard to take the electron to the excited state. Now, if only you can pull out an electron from the valence band, you can make the electron to freely conduct. Now, however energy you give, if you are not able to pull it out, there is no point in making that material conduct. So when you talk about an insulator, the band gap energy level is greater than 5 electron volt. So you need to introduce a very huge amount of energy to make that material conduct. So normally we won't go for this insulator when it comes for conduction purpose. The very reason is this. This is the physical reason behind avoiding insulator for conduction. Is it okay? Now, what is the primary reason for using silicon as a semiconductor material in most of the semiconductor device? The very first reason, it is available, abundant in earth. Okay, it's plenty. That is the very reason why we are going for silicon. Is it okay? Now, when you introduce an electric field to a semiconductor, the electrons start to move. It starts moving. Now, when it starts moving, automatically a term called mobility comes into the picture. So this mobility comes into the picture when the electron starts moving. And this movement is possible when an electric field is applied to the semiconductor. So, semiconductor and electric field is applied to the semiconductor. It results in movement of electrons, which results in mobility. Now, what is the when an electron is moving, obviously it's going to move in a particular velocity. Now, we call this velocity as a drift velocity. What is the relationship between drift velocity and the applied electric field? Drift velocity Vd is given by mu times E. Is expressed as Vd. It is given by mu times E. Okay, well, mu is the mobility of the electron and E is the applied electric field. Is it okay? So when electric field is applied to a semiconductor material, the electrons in the material starts moving with a velocity Vd whose mobility is mu. Okay, now this is actually applicable for an electron as well as for a hole. Now, coming to the magnitude of an electric field. Now, having given potential and having given a displacement of x, you must be in a position to find the magnitude of the electric field, which is given by E is equal to V divided by x. V is the applied potential and this x is the length of the material. Having known these values, you must be in a position to calculate electric field based on this formula. Now, what is the charge of the electron? A very important thing you need to remember. Q is equal to 1.6 into 10 to the power minus 19 coulomb. This is the charge of an electron. Okay, you must be in a position to know this. Now, suppose you have a specimen which is conducting a current I. For example, you have a specimen, it is conducting a current I. Now you have a magnetic field which is placed perpendicular to the current flowing. For example, you have a conductor, you have a specimen, you have a current flowing in the conductor, and you introduce a magnetic field which is acting perpendicular to the current flowing through the conductor, through the specimen. In this condition, you will have electric field induced in the specimen which is directly proportional to the, which is actually perpendicular to the direction of current and direction of the magnetic field. Okay, this theory is given by Hall effect. What is Hall effect? You have a specimen carrying current I which is placed in a magnetic field which is perpendicular to the current flowing. In this situation, you have electric field induced which is perpendicular, which is transverse to the direction of current and the magnetic field applied. This effect is called as Hall effect. Now, Hall effect is used to find whether the material is a p-type material or a n-type material. Is it a p-type or a n-type? Now, for finding whether the material is a p-type or n-type, you need to calculate the Hall voltage, which is given by VH, which is calculated by the amount of electric field applied and the displacement. E times G will give you the Hall voltage. Now, if the Hall voltage is positive, it's going to be a p-type material. If it is negative, it's going to be a n-type material. So if VH is positive, it's going to be a p-type. If it's going to be negative, it's going to be a n-type. Okay, so having given the Hall voltage, you must be in a position to find out whether the material is p-type or n-type. Now, if the Hall voltage is 0, exactly, it's going to be an intrinsic semiconductor. Whether it's a p-type or n-type or an intrinsic semiconductor, this can be calculated using the Hall voltage. Now, as I told you, we are going to now learn about the diffusion current density for a p-type as well as for a n-type material. See, current density is of two types: drift current density, diffusion current density. Now, I gave you the formula for drift current density, which is sigma E. Now, coming to the diffusion current density for a p-type, it is given by Jp, which is equal to minus Q dp dp by dx. Similarly, this is for a p-type. For a n-type, it is given by Jn is equal to positive Q dn by dx. Now, this diffusion current density comes into the picture because of change in concentration with respect to the distance. That is why I have a quantity present in this equation, dp by dx, dn by dx. The rate of change of hole concentration or the electron concentration with respect to the distance. Okay, this results in the diffusion current density quantity. Is it okay? Now, what is Q? Q is the charge of the electron, and diffusion coefficient is given by dp and dn. For a hole it is dp, for an electron it is dn. dp by dx is the rate of change of hole concentration, and dn by dx is the rate of change of electron concentration. Now, for example, distance 0, at a distance 1, at a distance 0 it is 10 to the power 18, at a distance 1 it is 10 to the power, for example, 19. Then the rate of change of concentration is 10 power minus 19 minus 10 to the power 18. Okay, so this is the change in concentration, which is given by dp by dx or dn by dx. So you must be very clear in this concept. Now I'm going to tell you the relation which is used to calculate the conductivity, resistivity and resistance. Now, conductivity is given by a term sigma, which is equal to NQ mu. I already came across this term. The conductivity, which is given by sigma, can be calculated from N, Q and mu, where N is the concentration of electron, Q is the charge of electron, and mu is the mobility of the electron. Is it okay? Now, having given a conductivity, how to find the resistivity? You must be very well knowing this. Inverse of conductivity is resistivity, inverse of resistivity is conductivity. So resistivity, it is given by the term rho. It is going to be equal to 1 by sigma. The inverse of conductivity will give you the resistivity. Now, what is the formula to calculate resistance? Resistance R is given by rho L by A. What is the resistivity or what is the resistance of a material? If they ask, you must find out the resistivity of the material, length of the material, area of the material. Having known, you can find out the resistance. Now, when you look here, the resistance is directly proportional to the resistivity. It is directly proportional to the length. So, more the length, more the resistance. Smaller the length, lesser the resistance. And also it is inversely proportional to the cross-sectional area. So if the area is large, its resistance is going to be small. If the area is small, its resistance is going to be large. That's why in the conducting wires, the power cables, in order to reduce the resistance, they go for a bigger cross-sectional area. That's the reason why it becomes heavier. The cross-sectional area increases, the material becomes heavier, and what's the reason for doing that? In order to reduce the resistance. Understand? Okay, now we go for solving some of the gate questions. Now, here is a question. Consider a silicon sample doped with Nd. This is a 2014 question. Consider a silicon sample doped with Nd is equal to 1 into 10 to the power 15 per centimeter cube. So Nd is given. It is equal to 1 into 10 to the power 15 per centimeter cube. Donor atoms. Assume that the intrinsic concentration Ni is 1.5 times 10 to the power 10 per centimeter cube. So here Ni is given 1.5 into 10 to the power 10 per centimeter cube. Now, if the sample is additionally doped with Na, 1 into 10 to the power 18 per centimeter cube. So it's given Na 1 into 10 to the power 18 per centimeter cube, which is acceptor atoms. So donor atom is, the donor concentration is given, the acceptor concentration is given, Na. And here you are asked what is the approximate number of electrons in the sample? What is the approximate number of electrons in the sample? Now, for finding this, first we need to find out the net holes. What is the total amount of holes existing in the material? Now that can be computed by the difference. See, this is the acceptor impurity, this is the donor impurity. The difference between the acceptor impurity and the donor impurity will give you the net holes. So it's going to be Na minus Nd, which is going to be equal to 10 to the power 18 minus 10 to the power 15 per centimeter cube. Now it's going to be equal to 999 into 10 to the power 5 per centimeter cube. Okay, this is the total hole concentration existing in the material. Now, we know the hole concentration, we know the intrinsic concentration, we can find out the electron concentration. What is the formula? N times P is equal to Ni square. Now we know P, we know Ni, we can compute N. So N is equal to Ni square by P. Ni is given as 1.5 into 10 power 10 divided by P is 999 into 10 power 5. Now the value is going to be equal to 225.22 per centimeter cube. Okay, this is one example problem of how we can calculate the electron as well as the hole concentration having given the intrinsic concentration. We will also solve one more example in this section. Yes, here a question is given. It's also a 2014 question. A silicon bar is doped with donor impurities Nd, which is equal to 2.25 into 10 to the power 15 atoms per centimeter cube. So the donor concentration is given in the question. It is 2.25 into 10 to the power 15 atoms. Given the intrinsic carrier concentration of silicon at 300 Kelvin as Ni is equal to 1.5 into 10 to the power 10 per centimeter cube. So Ni is given, which is 1.5 into 10 to the power 10 per centimeter cube. And assuming complete ionization impurity, the equilibrium electron and hole concentration is. So you are asked to find the electron and hole concentration in the equilibrium state. That is, what is the concentration of N? What is the concentration of P? Now, I already told you, having given the donor concentration, the electron concentration is approximately equal to the donor concentration. So I would say the electron concentration is straight away given in the problem itself. So the answer, a part of the answer is available in the problem itself. But if you only know this theory basics, you can able to identify the answer. So straight away we can write N is equal to 2.25 into 10 to the power 15. We got one answer. Now what is P? What is the value of P? Now I told you, having known the intrinsic concentration and having known the electron concentration, we must be in a position to find out the whole concentration. What is the formula? N times P is equal to Ni square. So we will know the value of N. We need to know the value of P, which is Ni square by N. Ni is nothing but 1.5 into 10 to the power 10. And the electron concentration is 2.25 into 10 to the power 15. So the whole concentration is the ratio between these two quantities, which is computed, and it is found to be approximately, this is whole square, so it is found to be 10 to the power 5 per centimeter cube. Okay, so you have to be very careful. Centimeter cube, the whole square, by centimeter cube. So it's going to be centimeter cube, the unit. Okay, so what is the electron concentration? 2.25 into 10 to the power 15. Whole concentration 10 to the power 5 centimeter cube. Okay, so having given an intrinsic concentration and donor concentration or acceptor concentration, you must be in a position to find out the electron concentration as well as the whole concentration. It's very simple. It takes less than a minute to solve this, if only you know this simple fundamental formula. We will try to solve one more problem. Now, the problem is, at T equal to 300 Kelvin, the band gap and the intrinsic carrier concentration of GaAs are 1.42 electron volt and 10 to the power 6 centimeter per centimeter cube respectively. So here it is given, band gap energy is given, it is given as 1.42 electron volt, and the intrinsic concentration Ni is given 10 to the power 6 per centimeter cube. In order to generate electron hole pairs in GaAs, which one of the wavelength ranges of incident radiation is more suitable? So you are given a range of wavelength. A is 0.42 micrometer to, I could reduce it, 0.42 micrometer to 0.87 micrometer. This is the first option. 0.87 micrometer to 1.42 micrometer, the second option. 1.42 micrometer to 1.62 micrometer, the third option, and 1.62 micrometer to 6.62 micrometer, the fourth option. So the energy band gap level is given, the intrinsic concentration is given. You are asked to find out the wavelength. Which one of the wavelength of incident radiation is more suitable? As I told you, when a wavelength lambda, when a light of wavelength lambda is incident on the atom is taken from the ground level to the excited level. The energy difference between the ground level and excited level is what? Given by Eg, which is 1.42 electron volts. Now, having given this input, what will be the wavelength range of the incident light, which is a correct range? You have to find out. The very fundamental formula is Eg must be less than equal to 1.24 divided by the wavelength, or wavelength is lesser or equal to 1.24 divided by the band gap energy. So it is equal to 1.24 divided by 1.42, 1.24 by 1.42. So your lambda must be lesser or equal to, the value is 0.87. So your wavelength of light, which is incident on the atom, must be lesser or equal to 0.87. It should not become greater than this wavelength. If it becomes greater than this wavelength, this energy band gap level cannot be achieved. Now coming to this option, we have 0.42 to 0.87, 0.87 to 1.42. These two definitely are not the right answer. Now coming to the option, it should be lesser or equal to 0.87. Here the range is greater than 0.87. So the first option must be the right option, because your wavelength should be lesser or equal to 0.87. Yes, okay, so the option A is the right option. So it's a very simple formula. That's why I quoted this formula in the beginning. The band gap energy must be lesser or equal to 1.24 divided by the wavelength that is incident on the atom. Now, coming to one more problem. This is also a 2014 question. At T equal to 300 Kelvin, the whole mobility of the semiconductor mu P is given as 500 centimeter square per volt. So you are given the mobility of the hole. It is 500 per centimeter square per volt, and you are also given the value of kT by Q. It is found to be 26 millivolts. Having given the mobility and kT by Q, what is the expression to define kT by Q? VT, thermal voltage. I already told you it is 26 millivolt in the room temperature, and it varies based on the room temperature variations. Having given this data, you are asked the whole diffusion constant dP, or diffusion coefficient. What is the diffusion coefficient dP? Okay, this is the question asked. So this is Einstein relation. If you use Einstein relation, you can find out the answer. What is Einstein relation? dP by mu P is equal to kT by Q. Okay, you are asked to find dP. So obviously dP is equal to kT by Q times mu P. So what is kT by Q? It is 26 millivolt times the mobility of the hole is 500 centimeter square per volt. So the product of these two will give you 13 centimeter square per second. Okay, so this is the right answer. This is actually a fill in the blank question. So if you know the thermal voltage and the mobility, you must be in a position to find out the diffusion coefficient. So this Einstein relation is a relation which is used to find out the mobility or diffusion coefficient having given either of the data. Okay. Now, again a question which is based on the energy level and the wavelength. The cutoff wavelength of the light that can be used for intrinsic excitation of a semiconductor material of band gap Eg equal to 1.1 electron volt is dash. The band gap energy is given 1.1 electron volt. Having given electron band gap, you are asked to find out the cutoff wavelength, which means the maximum wavelength that can be used to introduce this band gap energy. Okay, cutoff wavelength is the maximum wavelength that can be used. So it's a very simple question, and it can be answered if you know the relation. What is the relation? Lambda must be less than or equal to 1.24 divided by the energy band gap. So here it's gonna be less than or equal to 1.24 divided by 1.1, which means less than or equal to 1.12 micrometer. Now, by default, Eg takes electron volt units and lambda takes micrometer unit. So this could be the wavelength limit. It should be lesser or equal to 1.12 micrometer. Which means, what is going to be the maximum wavelength? It's going to be 1.12 micrometer. So lambda max is equal to 1.12 micrometer. Is it okay? So based on the formula, you can compute it in a very easy way. Now, yes. Here is a question. Drift current in semiconductors depends upon option A, only electric field, option B, only carrier concentration gradient, option C, both electric field and carrier concentration, option D, electric field and carrier concentration gradient. Now, I have given you the formula for drift current density. It is given by J. It is equal to N Q mu, and your drift current is given by N Q mu E. Now when you look here, it is proportional to the concentration as well as electric field, not the concentration gradient. So the right option among them, only electric field no, only concentration gradient no, electric field as well as carrier concentration must be the right answer. Carrier concentration is given by N, electric field is given by E, so the right answer could be electric field as well as carrier concentration. Now, the ratio of mobility to the diffusion coefficient of a semiconductor has the following units. You are given 4 units. A is volt inverse, B is centimeter volt inverse, C is volt centimeter inverse, D is volt second. These are the options given for mobility to diffusion coefficient ratio. Mobility to diffusion coefficient. We must be finding out the right option. Mobility to diffusion coefficient, mu by D. For mu by D, what is the right option? Units. Now, we very well know that dN by mu n, Einstein equation you need to use. dN by mu n is equal to dP by mu p is equal to kT by q, which is equal to Vt. And what is the unit for Vt? Vt is the volts. Now, dN by mu n is Vt means mu n by dN is going to be equal to 1 by Vt. If Vt takes volts, 1 by Vt takes volt inverse. So the right answer could be A. Volt inverse is the right answer for mu by D ratio. Now coming to another question, it's a 2007 question. The electron and hole concentration in an intrinsic semiconductor or Ni at 300 Kelvin. If acceptor impurities are introduced with a concentration of Na, the electron concentration per centimeter cube at 300 Kelvin is. So it is given the semiconductor has an intrinsic concentration Ni, and it is also added with acceptor impurities whose concentration is Na. Having given these details, you are asked to find out the electron concentration N. Okay, now this can be approximately equal to P, and N times P is Na square, so N is going to be equal to Na square by P, which is Na square by Na. So Na square by Na is the right option, which is the electron concentration of the semiconductor. So option D is the right option, Na square divided by Na. So it's very interesting, and if only you know the fundamental formulas, it's so easy to calculate the results. Yes. Now, here is a question. The concentration of minority carriers in the extrinsic semiconductor under equilibrium. The concentration of minority carriers in an extrinsic semiconductor under equilibrium is, this minority carriers concentration is, option A is directly proportional to the doping concentration. B is inversely proportional to doping concentration. C directly proportional to intrinsic concentration. D inversely proportional to intrinsic concentration. Directly proportional to doping concentration, inversely proportional to doping concentration, directly proportional to intrinsic concentration, inversely proportional to intrinsic concentration. You have to use the very fundamental formula. N times P is equal to Na square. So here it is asked the concentration of the minority carriers, so which is P is equal to Na squared by N. So this is the formula. The concentration of the minority carriers is directly proportional to the doping concentration, inversely proportional to doping concentration. Now, N is the doping concentration. Based on this equation, is it directly proportional to inversely proportional? It is inversely proportional. Now, we have to go through all the options before concluding which one is the right one. Third option is directly proportional to intrinsic concentration, but here it is directly proportional to the square of the intrinsic concentration. So this cannot be the right option, though it seems to be a right one. Okay, so the right option, the approximately the exact answer could be inversely proportional to the doping concentration. So B is the right answer. So all these problems that we solved is based on the very fundamental equation N times P is equal to Ni square. Now, coming to another problem. Here is a simple question. The band gap of silicon at the room temperature is option A 1.3 electron volt, B 0.7, C 1.1, D 1.4. So I have given you the inputs. For a silicon, what value? For germanium, what value is given? For a silicon, it is 1.1 electron volt. So if you could put it in your mind, you can just use it. You don't need any formula to actually calculate this. Now, N-type silicon is obtained by doping silicon with. Here it's a very important question. N-type silicon is obtained by doping. So, when will you get a N-type material? If you add a N-type impurity, you can get a N-type material. Now, the option given is germanium, aluminium, boron, phosphorus. Germanium, aluminium, boron, phosphorus. Now, among the four, which one is actually rich in electrons? I've given you phosphorus is the material which is rich in electron, and it is very important example given to you for N-type impurity. So phosphorus is the right option. Coming to the next problem, I have a question here which is a 2004 question. The impurity commonly used for realizing the base region of a silicon NPN transistor. The impurity that is commonly used for realizing the base region of a silicon NPN transistor. Now, emitter, base, collector. So you need to go for a p-type material for wisely choosing the base material. So the option given are gallium, indium, boron, and phosphorus. These are the four options given. Now, if you come to the options given here, the material that is rich in holes, the material that is rich in electrons is phosphorus. The material that is rich in holes, I have given you a list, and in that list, boron also one of the material. So among the four options, boron is the right option, because phosphorus definitely cannot be the right option because it is rich in electron. Just very recently we dealt and questioned based on this. So boron is an atom which is rich in holes. So we need to go for a p-type material for building up the base region. Is that okay? Now, here again, there is a problem. The intrinsic concentration of a silicon sample at 300 Kelvin is 1.5 into 10 to the power 16. Intrinsic concentration is given, which is 1.5 times 10 to the power 16. After doping, the majority carriers is 5 into 10 power 20. So majority carriers means it is Nd, donor impurity, which is given by 5 into 10 to the power 20. Now the minority carrier density is what is the question. So majority carrier, minority carrier is equal to Ni square. Now N is approximately equal to Nd. So we are asked here to find out the minority current density, carrier density. So which is P, which is Ni square by N, which is Ni square by Nd. We know the value of Ni, which is 1.5 into 10 to the power 16 the whole square divided by Nd, which is 5 into 10 power 20. So the ratio between these two values would give you the value which is equal to 4.5 into 10 to the power 11. Obviously centimeter cubic. Okay, so this formula is a very, very important formula you need to remember for finding the electron and hole concentration in a given semiconductor. Now, here is a problem, another problem. In a p-type silicon sample, the hole concentration is 2.25 into 10 to the power 15 per centimeter cube. It's a 1995 problem. It is given the hole concentration 2.25 into 10 to the power 15. This is the whole concentration given, and the intrinsic concentration is 1.5 into 10 to the power 10 per centimeter square. You are asked to find out the electron concentration. Hole concentration is given, intrinsic concentration is given, electron concentration is asked. So electron concentration into hole concentration is Ni square. So electron concentration is Ni square by P, which is equal to 1.5 into 10 power 10 the whole square divided by 2.25 into 10 to the power 15, which is equal to 10 to the power 5 atoms. (1.5) the whole square will become 2.25. So 2.25 is cancelled to 1. 10 to the power 10, the square is 20. This goes up, minus 15, 20 minus 15, 5. Is that okay? Simple mathematics and simple formulas which will fetch you good marks. That's the beauty of semiconductor physics. Here is a problem. This is the last problem. A small concentration of minority carriers is injected into a homogeneous semiconductor crystal at one point. An electric field of 10 volt per centimeter is applied across the crystal. So the applied electric field is 10 volt per centimeter. And this moves the minority carriers a distance of 1 centimeter. So the distance moved is 1 centimeter in 20 microsecond, so the time given is 20 microsecond. For applied electric field, this minority carriers is moved to a distance of 1 centimeter in 20 microsecond time. Having given this input, what is the mobility? What is the mobility? Now, what is the formula for mobility? Mobility is directly related to the drift velocity. Drift velocity is mobility times E. So if we could know the drift velocity, we can find out the mobility, because electric field is by default given. So mobility is drift velocity by electric field. But in the question, the drift velocity is not straight away given, but the velocity is indirectly given by some other parameters: distance, time. So what is velocity formula? Velocity is displacement by time. So you have 1 centimeter distance, 20 microsecond time. So your velocity is going to be equal to 10 to the power 6 by 20 centimeter per second. Because microsecond is 10 to the minus 6, it goes to the numerator, becomes 10 to the power 6. This is the velocity. Now we can calculate mu, which is velocity divided by E. So 10 power 6 by 20 times the electric field, which is 10 volt per centimeter, whose value is 5000 centimeter square per volt second. 5000 centimeter square per volt second. This is going to be the answer. Okay, so having given the drift, having given the electric field displacement at time, you must be in a position to find the drift velocity, and having known the drift velocity, you can calculate the mobility using the fundamental formula: mu is equal to Vd divided by E. So thank you all for watching this video. Hope you all understood. Please feel free to write your comments and ask your questions. Thank you so much.